Recently in class, we've been talking a lot about ramps because they're a great way to investigate objects which change their velocity, either naturally increase in speed when they go down the ramp or decrease speed on their way up the ramp. Well, today I want to ask the question, why does a car, a low friction car, when released from rest, naturally increase in speed when it goes down the ramp? Think about it. We've spent a lot of time describing the motion with graphs, position, velocity, and acceleration graphs, diagrams we call motion maps, and even algebraic equations to quantitatively measure the acceleration of something when it's on a ramp, either increasing speed or decreasing speed. But why is it that something naturally increases in speed? Well, if you think about it, we probably all want to blame whatever we call gravity. Up until this point in class, we've not talked a lot about gravity, and we're going to spend a lot more time talking about it. But it seems like we could probably all agree that we would say gravity is what's causing this car to naturally increase speed on the way down the ramp or to accelerate. It's changing its velocity. A second question we could ask would be, what's the quantitative acceleration that gravity can give this car specifically on this ramp? Well, we could use a motion detector to get a quantitative position, velocity, and acceleration graph, look at the slope of the velocity versus time graph, or what the acceleration is to get that specific value. So on this ramp, if I let this thing go, and we used our motion detector, we'd find out that this car has an acceleration of about 0.8 meters per second each second. So gravity can increase the speed of this car by about 0.8 meters per second each second that it's moving down this incline. Do you think there's anything we could do to this setup that would allow gravity to give this car a different acceleration than 0.8 meters per second per second? Well, if you think back to our spinner lab, we've already found out that as we increase the angle of the incline, that gives the object moving down that incline a greater acceleration. So if we increase the angle of this ramp, we would expect that this car would have a greater and greater acceleration. Well, gravity can't give this thing an infinite acceleration. Like, what's the maximum steepness and therefore the maximum acceleration gravity could give this object? Well, if we made this thing steeper and steeper and steeper, this is as steep as it gets, right? Straight up and down. And so if we have this track oriented vertically like this, we put the car on our track and use our motion detector and basically dropped it, what we would measure to be the acceleration would be the maximum acceleration that gravity can give this particular object. Right? Well, once we get the track all the way up and down like that, that's not really any different than just having a motion detector like this and dropping an object underneath it to measure its maximum acceleration. What we're going to be looking at in this video is the maximum acceleration gravity can give a freely falling object, meaning the only thing affecting it is gravity. So we're going to figure that out for something like a car that has a mass of about 2.5 kilograms. Or let's say the maximum acceleration that gravity can give a soccer ball, 0.35 kilograms. Or we'll find out if we have something as massive as a bowling ball, about 7 kilograms, what's the maximum acceleration gravity can give this object? Are they different based on their mass? Are they similar? Are they the same? Like, that's one of the things that we're going to figure out. We're going to try to do this using 4 different objects. 3 different mass bowling balls, and a small mass soccer ball. So here are those 4 balls being dropped at the same time. I have them all side by side so we can compare how each of them falls. How does gravity influence the motion of each of them as they each speed up towards the Earth in the negative direction? So you can see it in real time for a little bit, but then I slowed it down so we can see frame by frame. And what is it that you notice? It seems like the 7 kilogram mass, the 4.5, the 2.7, and the 0.35 kilogram mass are more or less falling down the same amount each frame. So they're increasing in speed in the same way, which means they're probably changing their velocity by the same amount each and every second. It seems like no matter what the mass is, larger mass or smaller mass, it doesn't seem to affect the acceleration that gravity gives each of those objects. So if we want to measure the maximum acceleration that gravity can give any object, apparently all we need to do is measure it for one object, because regardless of mass, each of those objects have the same acceleration. So here I've got that same video of the 4.5 kilogram bowling ball that I dropped, and I have it within a software program called Logger Pro. This is a tool you'll end up using later in the semester for another investigation. So in Logger Pro, you can insert any video to basically do what's called a video analysis. We can analyze the motion of an object moving in a video, kind of like you guys did with the toy car lab or the ramp lab with the spinner, where you could advance something through frame by frame to figure out where it was at specific times. Well, Logger Pro can do that same thing, but it's a little bit more advanced. So we can click this through frame by frame, starting from the beginning. We could click it through frame by frame, and it has some tools which actually allow you to mark the location of the object each and every frame, not just a few random frames like you guys did, but every single frame. And I've already done that. Clicked it through frame by frame, and that blue dot shows where I was marking the location of the bowling ball. And if I click it through all the way to the end, each of those frames, click this button, it shows you the record of where I clicked throughout its entire motion. And because we know something of known length, I put a meter stick in there so we knew that this was 1 meter long. These dots in the video measured by pixels, and knowing this 1 meter length, Logger Pro is able to calculate at each specific time the horizontal position of the bowling ball, that's the X position, the vertical position, that's Y, how fast it's moving in the horizontal direction, that's the X velocity, and what the velocity is in the vertical direction, that's Y velocity. So just from scaling the video and marking the location of the object, we've got all of this data. And now that we have this data, we can graph it to see what the shape of the graphs are and get some quantitative measurements like what we're after, the acceleration that gravity's giving that bowling ball. So let me come over to the graph, and I'm going to put on the y-axis, I'm going to put y, which stands for the vertical position. So let's just make sure this makes sense. So this says at time 0, the bowling ball is about 3 meters above the ground. So from here to there, it's about 3 meters. And you can see that as time goes on, the vertical position is getting smaller because the ball is falling closer to the ground. And you can see that it's not a straight line. It's getting steeper and steeper and steeper, which is what we would expect because the bowling ball is speeding up as it falls towards the ground. Let me now graph the y velocity versus time. So what's true of the vertical velocity versus time? Let me change the scale just a little bit so we can see all of our data. Okay, so here's the 0 axis. This is velocity versus time. See that the velocity was measured a little bit after time 0, a little bit after the moment I released it because it doesn't start at 0. But you can see that the velocity is decreasing. It's getting more negative as time goes on, so it's speeding up in the negative direction. And you can see that gravity apparently changes the velocity linearly. Gravity gives the bowling ball a constant or uniform acceleration because the velocity time graph, it's linear. So if we want to figure out the acceleration that gravity gives this bowling ball, or the maximum acceleration during free fall, we just need to find the slope of this velocity versus time graph. Logger Pro has quite a few cool tools, and one of them is just adding a linear fit. But I'm just going to take my cursor and select the data points and add a linear fit to that. Looking at the slope of our line of best fit, we can see that it's about negative 9.7 meters per second each second. So that's the acceleration gravity is giving the bowling ball. Negative 9.7 around negative 10 meters per second. And we would have found that for any of the bowling balls because like we just saw previously, they all fall the same. I'm not sure if that was a surprise to you, but it is a little surprising if you think about it. This massive bowling ball with about 7 kilograms of mass has pretty much the same acceleration that we could tell as this 0.35 kilogram soccer ball. That's greater than 10 times difference, and they have about the same acceleration. So our observations and analysis suggest that no matter what the mass of an object is, they'll have the same acceleration. They would fall together if released from rest at the same time. So that suggests that this textbook, if dropped, would have an acceleration of about negative 10 meters per second each second. Or if I jumped up on this table and let myself fall freely, just kind of drop from rest, that my mass, which is even 10 times more massive than this bowling ball, would have about the same acceleration. Now, some of you might be thinking, that doesn't seem to make sense. Like, I get it, our observations seem to suggest that, but there's not everything falls the same. Like if you think about it, a feather, right? If I dropped a feather, it's going to kind of float down. I don't have a feather with me, but I have a sheet of paper. And let's just see, how does this sheet of paper fall compared to our textbook? Right? Very clearly, this thing does not keep pace with the textbook. There's something that's not allowing this thing to speed up nearly as much. Well, what could that be? Well, everything that's falling towards the earth, fortunately, is falling through air. We need that to breathe. We need that to survive, right? Well, apparently, this paper, because it's not very massive, there's a greater impact on its motion. The air particles have a greater impact on its motion than it does the textbook, because anything that falls through the air has to kind of spread out and get away from it. So it's contacting air particles on the way down, and apparently they're resisting this more. It affects its free fall motion a lot more. So let's think about this. Is there anything we could do to this piece of paper that would maybe minimize the effects of that air resistance, the resistance the air is providing on this sheet of paper as it falls through? Well, if it's based on the collisions of the air particles as this thing falls, can we do anything to decrease the number of collisions? Well, we could crumple it up. Crumpling it up means it's not going to hit nearly as many air particles on the way down. Maybe it's going to minimize that effect of air resistance. So with this crumpled up, let's find out. This is much less massive than this textbook, right? Maybe by like 1,000 times. Do they fall similarly? Okay, you can see they pretty much fall together. So if air resistance is minimized, the effects of air resistance are not significant, we'd say that they're negligible. That means this small mass piece of paper, this textbook, me, this soccer ball, this bowling ball, no matter what the mass of an object is, if air resistance is not significant and the object is in free fall, it's under the influence of gravity alone, those objects will all have an acceleration of around negative 10 meters per second per second. That's pretty much going to be good enough of value for doing homework assignments in this class. But when scientists measure the maximum acceleration that gravity can give objects near the Earth's surface with precise instruments, we get a value for all mass objects around negative 9.8 meters per second per second. Like I said, when we do our homework assignments, negative 10 meters per second each second will be good enough. But if we're in a lab situation, or you guys are doing a lab challenge where you want the most precise measurement of the acceleration that gravity can give an object, definitely go ahead and use negative 9.8 meters per second per second. So now we can solve quantitative problems about objects that are speeding up as they fall towards the Earth. They're in free fall. We know that all objects, regardless of mass, have an acceleration in the absence of air resistance of negative 10 meters per second each second. Well, we can't quite be done there because gravity influences motion in terms of speeding objects up, but gravity can also slow objects down, right? If I were to take the soccer ball and just toss it up, what's the acceleration that gravity could cause when it's slowing something down, like when we throw this thing up? Similar to how we looked at how gravity sped things up, I've got a side-by-side comparison of two different mass objects to see how gravity slows each of them down. As they are moving in the positive direction, they're decreasing in speed, which means they should both have a negative acceleration. And you can see that gravity is affecting them the same, especially when you look at it frame by frame. And so it looks like the 7 kilogram object and the 4.5 kilogram object would have the same negative acceleration, both caused by gravity. So we're back in Logger Pro, so we can do a little quantitative analysis by analyzing the video, again using our 4.5 kilogram orange bowling ball. So just to show you again, here's the clip of the bowling ball slowing down as it moves up. Gravity's decreasing its speed. And if I click this on, you can see these are all the spots that I marked. You can see that the spacing is getting smaller as the ball goes up because the speed is decreasing. If we look at our vertical position versus time graph, it's increasing. And notice the slope is getting less steep. It's because the speed is decreasing. So let's go ahead and look at the velocity versus time graph. See that when I started collecting data, it was moving at positive 6 meters per second. It was moving up in the positive direction. As time goes on, gravity's decreasing the speed, bringing it back towards eventually a velocity of 0. Just like when gravity sped up the bowling ball, it's changing the velocity in a linear fashion. Gravity causes things to have a constant or uniform acceleration. And what is that acceleration? Well, let's just find the slope of our velocity time graph like before. Get the slope of our velocity time graph is, again, about negative 9.5. We got to think negative 9.6 last time. Gravity is giving this thing an acceleration of about negative 10 meters per second each second. And that's true even though it's moving up and slowing down. It's the same as when it's moving down and speeding up. So apparently, no matter what an object is doing, if it's in free fall, if it's under the influence of gravity alone, and it's moving either up or down, gravity gives the object the same acceleration, about negative 10 meters per second each second, or more precisely, negative 9.8 meters per second each second. Okay, we're going to look at two quick examples to see some of the implications of everything we've learned so far about how gravity affects the motion of objects, both that increase in speed while they're moving down and decrease in speed while they're moving up. So let's just deal with the dropped object first. If we have something that's dropped from rest, so its initial velocity is 0 meters per second, we found out that it's going to accelerate, it's going to change its velocity each second by about negative 10 meters per second. Which means if this bowling ball is dropped from rest 1 second later, it should be moving at about negative 10 meters per second. And then another second later, it should be moving at negative 20 meters per second. Remember, its velocity changes by negative 10 meters per second each and every second. That's what an acceleration tells us. So if we were to graph this on a velocity versus time graph, starting from rest, 1 second later, the next velocity will be, with the acceleration of negative 10, like we found experimentally, it'll be negative 10 meters per second. Then it'll be negative 20 meters per second. And then 1 second later, it will be negative 30 meters per second. And just like we saw in the video analysis, gravity causes things to change velocity in a linear way. It's a constant acceleration or a uniform acceleration of negative 10 meters per second each second. So if we have this quantitative graph, there's actually some more we can figure out about falling objects just based on this quantitative graph. Let's say we wanted to find out the displacement of this falling bowling ball if it's dropped from rest over the course of 2 seconds. So what is the displacement? Well, if we have a quantitative velocity time graph, how do we find the displacement over that time interval? We shade in the area between the velocity line and that 0 axis. And so we get a triangle right here. So this area right here will be the negative displacement of the bowling ball, how far down it's fallen in 2 seconds. Let's now look at the situation where we have something that's launched upward with an initial velocity of positive 30 meters per second. We saw with the video analysis again that the acceleration is also negative 10 meters per second each second. That's true of something moving in the negative direction and increasing in speed, or moving in the positive vertical direction and decreasing in speed. So what would the velocity versus time graph look like here? If the initial velocity is positive 30 meters per second, and the acceleration is negative 10 meters per second each second, that means every second later, the velocity has to go down by 10 meters per second. So if it starts at 30, it's going to go to 20. When it's at 20, 1 second later, it will be at positive 10 meters per second. And 1 second later, it will be at 0 meters per second. So that's at rest when it reaches its highest point. And so this thing's going to come to rest after 3 seconds. It also changes linearly like this, and so we can kind of fill in our line right here. Let's say we also wanted to define the displacement of this bowling ball in the first 2 seconds, from 0 seconds to 2 seconds. Again, we just have to shade in the area between the velocity, whatever's graphed, and the 0 axis. And if we shade that in for the first 2 seconds here, that's an area above 0, so it's going to have a positive displacement because the whole time this bowling ball was moving in the positive direction. And we'd have to find the area of this trapezoid, or to make our life a little bit easier, we could split it up into two geometric shapes, and the total displacement over the 2 seconds for the bowling ball moving up would just be the rectangular area plus the triangular area.